Hi everyone, this is Dr. C.S. Gauri from Department of Mathematics. Today we are going to see application of matrix. Matrix, we know that it's a branch of linear algebra. The system of equations can easily be represented in terms of matrix, and obtaining the solution using matrix method is quite easier. So we are looking for matrix today. Here one of the topic we are going to study is eigenvalues and eigenvectors. Before that, before going to the topic, what is the importance of this eigenvalues and eigenvectors? This eigenvalues and eigenvectors plays a vital role in engineering fields like data science, artificial intelligence, neural networks, etc. As we aware that vector, it's a quantity which has both magnitude and direction. So in order to transform, like when you are having a big data set, if you want to shrink the size of the data or in order to maximize the size of the data, so we use some transformation. So for that, the quantity is represented in terms of matrix and it is multiplied by another matrix. Then the resulting expression is sometimes it's a scalar. So suitably we have to multiply the given quantity by a matrix in which the resulting expression is a scalar. So this scalar we obtained is called the eigenvalue and the matrix we use to transform an object is called vector. So here this transformation does not go for like changing the position of the object. It just make a shrink or maximization or shear on this object. Okay, so with this small note we are going to see how to find our eigenvalues and eigenvectors. So when you look for the eigenvalues and eigenvectors, this eigenvector is denoted by x, capital X, and it's a column vector, and the eigenvalue is denoted by the scalar lambda. So if lambda is greater than 1, we are looking for the maximization. When lambda is less than 1, we are looking for shrinkness of the object. Then when you simplify this, Ax is equal to, and some procedure we are using to find out the eigenvalue and eigenvector. Actually, we are not looking for eigenvalues straight away. Actually, we are looking for eigenvector. So a matrix which is multiplied by an eigenvector, the resulting expression is a scalar multiplication. This scalar is called the eigenvalue. This eigenvalue just helps us how much shrink can be or how much maximization, how much shear can be take place. The amount of shear, amount of shrinkness, amount of maximization can takes place. So with this small note, okay, so let us see this ax is equal to lambda x. So on simplification, we get an expression ax minus lambda x is equal to 0, and in that determinant a minus lambda equal to 0 is called the characteristic equation. On solving this characteristic equation, we get some roots. When it is a 2 by 2 matrix, we can get 2 roots, and if when it is a 3 by 3 matrix, we can get 3 roots, right? So these roots are called the eigenvalues, and corresponding to each eigenvalue, you can find out eigenvectors. The eigenvalues for distinct, the eigenvector for the distinct eigenvalues are pairwise orthogonal. Okay, so first we are going to see uh, how to find out eigenvalue, eigenvector for a real symmetric matrix. Real symmetric matrix in the sense A is equal to A transpose. That is row elements is equal to column elements. So here it is a symmetric matrix. Here Aij is equal to Abi. Just minus 6, A12 place is minus 6, A21 place is minus 6, and A13 place is 2, and A31 place is 2. This is called symmetric matrix. So first I am looking how to find out eigenvalue. So the characteristic equation is what? Determinant A minus lambda equal to 0. This is obtained from the expression Ax is equal to lambda x. And the simplification of this determinant A minus lambda equal to 0 is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. So for instead of looking for a determinant A minus lambda I and its simplification, hereafter we use this expression lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0 for getting the eigenvalues, where S1 is the sum of the main diagonal elements. So here this is your main diagonal elements 8, 7, 3. Okay, here sum of the main diagonal elements is 18. Then we are looking for sum of the minors of the principal diagonal elements. So let us look for this in detail. Okay, with very careful. Main diagonal elements is 8. So the minor of 8 is this determinant 7 minus 4 minus 4 3. And next main diagonal element is this 7. So they leave this row and leave this column. So it is 8, 2, 2, 3. And next is the last diagonal element is what? 3. And leave this row and leave this column. And here the minor is what? 8 minus 6 minus 6 7. So how to easily remember na? Here first you are looking for these four elements like 7 minus 4 minus 3, and the next the four corners 8 2 2 3, and next is what? First four elements 8 minus 6 minus 6 7. Okay, here hope you studied how to find out determinant in your schooling. Actually, when you go for determinant, you use negative signs in the middle. But here there is no negative sign. It is simply sum of the minus of the main diagonal elements. So upon calculation, we are getting it as 45. And S3 determinant, you know that determinant is calculated by this expression 8 into minor 8, the minor of 8. Then in between you are using minus sign. So already there minus 6. So minus into minus plus 6. Then leave this row and leave this column. You're looking for minor of minus 6. It is minus 6 minus 4 2 3. Next we are looking for the minor of 2. So it is minus 6 7 2 minus 4. Then upon calculation we are getting S3 equal to what? 0. Substituting these values in the characteristic equation, lambda cube minus S1 lambda squared plus S2 lambda minus S3 equal to 0. We are getting lambda cube minus 18 lambda squared plus 45 lambda minus 0 equal to 0. So you can ignore minus 0 in the next line. So what you are getting is lambda cube minus 18 lambda squared plus 45 lambda equal to 0. Now you are solving this. Since lambda is common, you take it outside. So lambda into lambda squared minus 18 lambda plus 45 equal to 0. So lambda equal to 0 is one of the root. It's very obvious. And the remaining is the quadratic equation. The quadratic equation can be solved. Uh, so here you are looking for 45. So when you are taking two values and the multiplication of this is 45 and addition of the two values is what? Minus 18. It comes under 3 and 15. So it is minus 3 and minus 15. Just check lambda squared minus 18 lambda plus 45 you are getting. So the eigenvalues are 0, 3, 15. Right? Then here the eigenvalues are distinct. Sometimes you may get repeated two eigenvalues repeated, or sometimes you may get three eigenvalues are repeated. Let us see this later on. Okay, now we are looking for how to find out the eigenvectors. Okay, actually basic concept of this eigenvalue and eigenvector is Ax is equal to lambda x. So we are going to substitute this eigenvalue in this expression. The simplified form of Ax is equal to lambda x is what? A minus lambda I into x is equal to 0. So this is it. So the meaning of A minus lambda I is you are subtracting lambda from the principal diagonal elements. And this I you know it's a unit vector. So 8 minus lambda into lambda minus 6, 2, then minus 6, 7 minus lambda, minus 4, 2, minus 4, 3 minus lambda. And here the eigenvector is x1, x2, x3, 0, 0. Right hand side 0 0, and we are looking for eigenvector for each case. There are three eigenvalues, so you are looking for three vectors. Okay, when the eigenvalues are distinct, you for each case you can go. So when you put lambda equal to 0 in the expression A, we are getting 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 into this one. And you are looking for matrix multiplication 8x1 minus 6x2 plus 2x3 equal to 0 minus 6x1 plus 2x2 minus 4x3 equal to 0 and 2x1 minus 4x2 plus 3x3 equal to 0. And we are looking for the solution of x1 x2 x3. In order to find the solution, we are, instead of solving three equations, three unknowns, we are considering only two equations and we apply cross rule method. How to look for? So when we select the two equations, we should note that the two equations should be distinct. So here when you look at the first two equations are distinct, so I can go with first two equations. So how to use cross rule method? So when I look for the solution of x1, I am looking for the element that is leaving this x1 coefficient of x1 and leaving the coefficient of x1 in the uh, first and second equation. So next is minus 6, 7, 2 minus 4. And when I want the answer for x2, same way I am leaving the coefficient of x2 in the first and second equation. The rest is 2 minus 4, 8 minus 6. Similarly, if we want the solution for x3, I am leaving the coefficient of x3 in the first second equation and looking for remaining to 8 minus 6 minus 6 7. Okay. So instead of that, an easier way you can go with start with the second number in the equation minus 6 7 in both the equations minus 6 7 2 minus 4 8 minus 6 then minus 6 7 you end with where you started. Okay, then you go with like determinant minor method. So minus 6 minus 4 is 24, 24 minus 14. Likewise, x2 is what? Minus 12 plus 32. And x3 is what? 56 minus 36. So on simplification, you can get 10, 20, 20. So we are looking for the smallest eigenvector. So here 10 is common. You divide the values by 10. You can get x1 by 1, x2 by 2 and x3 by 2. Similarly, so the corresponding eigenvector is 1, 2, 2. Similarly, I can go for finding the eigenvector corresponding to lambda equal to 3. So, in the equation number A, you substitute lambda equal to 3. So, what do you get? 5 minus 6, 2 minus 6, 7 minus 5 is what? 2 minus 4. Then 2 minus 4, 3 minus 3 is what? 0. So what do you get on a simplification putting lambda equal to 3 we get again a 3 by 3 matrix like this and you form three linear system of equations and instead of solving we are looking for three equations three unknowns we are looking for cross rule method and here we select two distinct equations to get the solution. If you select the two equations as same na, then you are getting the solution as 0. So you avoid this case. And if an equation which consists of all the coefficients as 0 na, that too you avoid. So here the main objective is to select finding eigenvector. We have to select two distinct equations. So here I am looking for first two equations and cross rule I am using as we discussed earlier. We are starting with the second number of both the equations minus 6 4 2 minus 4 5 minus 6 minus 6 4 use cross rule method and here upon simplification 2 2 minus 2 again we want smallest eigenvalue since 2 is common so divide by 2 so the answer is what 2 1 minus 2. Okay, here it is 2, 1. Okay. Then similarly, we are looking for lambda equal to 15. So subtract 15 from the principal diagonal element and form the matrix. Then form the 3 by 3. That is 3 equations, 3 unknowns form it. Then we use cross rule method. Then we are getting 40 minus 40, 20. Then 2 minus 2, 1 is the corresponding eigenvector. So the eigenvector is what? 1, 2, 2, 2, 1 minus 2 and 2 minus 2, 1 corresponding to the eigenvalue 0, 3, 15. As we discussed earlier, when lambda is less than 1, This eigenvalue helps to shrink the given data space. Okay. Then greater than 1, it maximizes the state data space. So with this, we can end this session. Thank you.